Okay, in this video, I am going to be working through all the problems on the radical expressions and equations worksheet. Okay, so you should print that and then take good notes while I go through this so that you'll have some notes to use while you're trying to take your test on this. Okay, all right, so you already know a lot about finding square roots of things, but you don't really know what to do when there's variables under the radical or when you have things other than square roots like cube roots or fourth roots. Okay, you know how to solve, you know the beginnings of how to solve a radical equation, but the only ones you've dealt with are ones that involved a square root. Okay, so we're going to extend the ideas there a little bit. Okay. So I'm just going to go ahead and do this in order. All right, so one of the things that is interesting to know is that, that work we did in chapter 4 on exponents, how like 3 to the second power is 9, how 3 to the first power is 3, and then how 3 to the 0 power is 1. And then we even talked about negative exponents being fractions. All right, well, one of the things that's kind of interesting to note is that you can have an exponent that's fractional, like 3 to the 1/2. That really is the square root of 3. And if you did that, it would turn out to be around 1.41. Okay, so 3 to the 1/2 would fall somewhere in there, and its value would fall somewhere between 1 and 3. Okay, well, it turns out that the fractional exponents really correspond to radicals. Okay, so fractional exponents can be changed into radicals, or they have some connection to radicals. Right? So like 3 to the 1/2 we just did, that would be square root of 3. But if you had like 3 to the 1/5, then it would be the 5th root of 3. So up here on the square root of 3, we have an understood what they call index of 2. But then if it's bigger than that, you have to actually write it. But notice how the bottom number gives you what the root is. Okay. All right. So that's kind of the idea behind question numbers 1 and 2. Okay. So on problem number 1 on the worksheet, the problem looked like this, and it asked to rewrite in exponential form. So they gave it to you in radical form. Okay. So when you do that, what you want to think about is you're going to have x to the second, and it's going to be raised to the 1/3 power. See how the index was 3? That corresponds to the denominator of the fractional exponent. Now this one had the power on x inside there underneath the radical. Well, that 2 and that 1/3, they're just exponents. And when you have a power raised to a power, remember the shortcut was that you could multiply those. And so ultimately we get x to the 2/3. Now really you can do it a little easier than that when you see it. It's going to be x to the power over the root. Okay. All right, and that's all they wanted on number 1, so that would be the answer. Okay. And I'm just really wanting you to recognize that the notation for square root, cube root, and all of that really is like an exponent. You could rewrite it as exponents. Okay. All right, and then this number 2 goes in the reverse direction. It gives you negative 216 raised to the 4/3, and it says 2 things. It says rewrite in radical form and simplify. Okay. All right. So what I would do on this one is I would notice the denominator is 3. So that tells me the kind of radical I'm going to be dealing with. See how the negative 216 is in parentheses? So it's going to all be inside there like that. You don't need the parentheses on it when it's in there because the radical is a grouping symbol. And then the 4 up here would be what you're going to raise all of that to. So you could do it like this, or you could do it like this. Okay, you could do that either way. The top one is actually better because if something turns out to be imaginary, you'll know it. And also it'll keep the numbers a little bit smaller. Okay, so that winds up equaling a -6 when you do the cube root of negative 216. That's what number times it, you should be thinking what number times itself 3 times would equal 216, and that would be a -6. And then that has to get raised to the 4th power, and -6 times itself 4 times would wind up being 1296. Okay, so your final answer would be 1296. Rewriting it in radical form, that would be this box. Okay, so that was just a matter of, I just really wanted you to know that fractional exponents really correspond to radicals. All right, then we get into an area that you should be more familiar with. Okay, so when we're looking at like 3, 4, 5, and 6, where you're simplifying radicals, let's look at those. Okay. All right, so on number 3, you're being asked to simplify the square root of -98. No, that's not true. The negative's out in front. Okay, negative square root of 98. Okay, on number 4, we have a new type because the root is higher than you're used to. Okay, and then I have one where I'm asking you to do the cube root of 500. And then one more was negative 240. So this is problem number 6, square root of negative 240. So 3 and 6 are ones you've already had to do, but 4 and 5 have an index that's higher than you're used to. Okay, so let's take a look at these. So on number 3, you should be thinking, well, let me take the 98 and break it down. 2 goes in there 49 times. 49 is a perfect square. So those of you that understand the approach this way, you could do the square root of 49 and get 7 and then do the square root of 2. Okay. Or you could keep breaking it down until you get to the prime factorization. Okay. So you need to take the square root of this, right? And so you can see there's a pair of 7s. That makes it a perfect square. That makes it 49. So that's 7 on the outside and 2 underneath the radical. Or you could have stopped one step earlier and said 49 is a perfect square. The square root of 49 would be 7, and then we'd have the square root of 2. The negative doesn't cause you to get an I because it's out in front. So the simplest radical form of that would be -7 square root of 2. Okay. Now with this one, if you're trying to just think this through, it's asking you what times itself 5 times would be -243. Okay? And it might turn out to be a perfect power of 5. Okay, we're not sure, so we could take that -243. If there's a negative under here when this is odd, it does not cause you to get an I. It causes you to get a negative number. It's like each of these would be negative. And then multiplied all together, it would give you a negative. So you don't get an I, you get a negative number. All right, so usually I don't break down the -243, I just break down the 243. Okay, so let's see what happens when we do that. So if we divide by 3, we get 81. Oh, this is going to be 5 3s. Okay, I'm trying to do the 5th root of that. I've got 5 factors, and that's what I'm looking for is 5 when it was square root. When this was square root, I'm looking for 2 multiplied together that will make that happen. When it's a 5th root, I'm looking for a pair of 5 3s multiplied together. So that means that's going to just be 3. Okay, but really it's -3. So this one would be -3. So what I'm claiming is that -3 times itself 5 times would give me -243. So number 4 was a perfect power of 5. Okay. All right. Now let's look at the cube root of 500. Okay, so again, we're not doing square root, we're doing cube root. So we're looking for things times themselves 3 times that would make that happen. Okay, so let me take the 500 and break it down. That'd be 5 times 100. It'd be 5 times 20. That'd be 5 times 4, and then there's 2 2's there. So we have 1, 2, 3 5's times 2 2's. Okay, so that's completely broken down. That just helps me be able to see all the pairs of factors. So if I'm trying to do the cube root of that, I'm looking for groups of 3. And see that group of 3? That's how you identify a perfect cube. So 5 times 5 times 5 is really 125, isn't it? So the cube root of that would just be 5. Okay, so the cube root of 125 is 5. You're looking for a group of 3, and then you can bring them out in front. But you see how there's only 2 of them, so they stay trapped underneath. And so that would be 5 cube root of 4. This would be 5 cube root of 4. Now, one of the mistakes I make that really irritates me is I forget to put the index of 3 in there. You really need to do that. You need to put the index of 3 in there, okay? All right, now let's look at number 6. That should be more familiar to you. It's a square root, so it's an understood index of 2. It does have a negative underneath the radical. Okay, so that means this one right here is going to have an I. It's imaginary, so it's going to have an I in it. All right, so normally I get that out of the way right off the bat. Like I already can see that this is going to be an I. So now I'm just going to take the 240 and break it down. However you get started is fine. All right. So I have 1, 2, 3, 4 2's, a 3, and a 5. Okay. So if I'm doing square root, I need pairs. So here's a pair. Here's a pair. 3 and 5 don't have a pair, so they're going to be trapped underneath. I'm going to put them back together for 15. Then by getting a pair, I know 2 times 2 is a perfect square. So that's 4. I can bring a 2 out. 2 times 2 is a perfect square. That's 4. So I can do the square root of that and get a 2. So out in front, I'll have a 4 with square root of 15 left. Now, I got to remember there was an I, though, right? So when I go to write my final answer on this one, my final answer is going to be, this was 4 square root of 15. This was I. So my final answer would be 4I square root of 15. Okay. All right, so that's problems 3, 4, 5, and 6. So the new ones, the ones that were a little extension from what you already knew, were the kind that had an index that was different than a 2. So you had to be looking for groups of 5 when it was an index of 5. Or when it was an index of 3, you're looking for groups of 3. But the concept is exactly the same. So just take some time thinking about that. Okay. I'd like to go ahead and do the other 2 problems on that page, and then I'll stop the video so it doesn't get too long and we'll continue. Okay. All right, so let's take a look at question number 7 and 8. They're both kind of the same type of thing. So on number 7, oops, sorry, go back to my whiteboard. So on problem number 7, I was trying to change the color back to blue. Okay, on number 7, the problem was to find the unknown length. So we had this right triangle. We knew this information. It's not drawn to scale. And it says write the answer in simplest radical form. Okay, so it said to write answer. So you're supposed to find b is basically the unknown length. So what this has to do with is the Pythagorean theorem, okay? The Pythagorean theorem says that if you take the two shorter sides of the triangle and square them, add them together, that they're going to equal the longer side squared. So that's in general, and I showed that on the answer sheet I gave you. So if you have any right triangle with the short sides labeled A and B and the long side labeled C, then you know that A squared plus B squared always equals C squared, but that's if it's a right triangle, which it is. All right, and then it's just a not that hard of an equation to solve. So you know 4 plus B squared is equal to 64. Okay, I can subtract the 4 from both sides. When I do, I'll get B squared equaling 60. Right, and then this is a quadratic equation. I learned that I can just square root both sides. This is a perfect candidate for that. So I'd have to do both the positive and negative square root technically. And so I'd wind up with b equaling positive or negative, and I got to break down that 60 like I've been doing. And I get a 2, a 2, a 3, and a 5. So when I do the square root of that, I got a pair of 2s. So it'll be a 2 outside with a 15 underneath. All right, now when you say what your final answer is, we are in a context where only the positive one makes sense. So your answer would be 2 square root of 15. And that's what they're talking about when they say simplest radical form. So this was just an example. The Pythagorean theorem is used to find missing parts of a right triangle, and it requires radicals. Okay, so it was just an example they were using to show you why you need to simplify radicals. Okay, another example comes from the distance formula. You will not be expected to know this formula, but it's just nice to know there's a reason for doing things. So for instance, if I was trying to find the distance between the point 4, negative 2, which would be like right here, and the point 2, negative 6, continue that, 5, 6, 2, negative 6 right here. I'm trying to find the length of this line segment. It's really just an application of the Pythagorean theorem. I could make a right triangle, and I would know this, and I would know this, and I would just be looking for that piece. But rather than going through all of that and having to draw a graph, it turns out that you can use the distance formula, okay? So the distance formula is really just the Pythagorean theorem written in a slightly different way. D is actually what they're calling this side right here. So in the formula, when they talk about D, it's the distance between 2 points. Okay. And so it turns out to be the difference in the x. Oops, I didn't mean that to say squared. I meant for it to be a subscript. It's the difference in the x coordinates squared and the difference in the y coordinates squared. And so when you do the difference in the x coordinates, that's this piece here. You don't really have to understand this. I just think it helps to kind of get the sense of it. That would be this spot, and the difference in the y coordinates would be this. And so what you're really doing is doing a squared plus b squared equals c squared, and then you're just square rooting it. Okay. But anyway, so just use the formula. So I'm just going to plug in the coordinates of the points. So they gave me the coordinates of the points. They said one of them was the point. Find the distance between these 2 points. One of them was 4, negative 2. The other one was 2, negative 6. You really would not have to draw the graph over here. You could just plug into the formula. So the distance would be, and it doesn't matter which point you consider the first point, just make sure you keep the x's together and keep the y's together when you do your subtraction. And watch all the negatives. That usually gets people. So this formula has minuses in those 2 spots. The rest of the negatives just come from the points themselves. Okay. So 4 minus 2, that would be 2 squared. Negative 2 minus negative 6, that's negative 2 plus 6. So that's going to be 2 squared plus negative 2 plus 6 would be 4 squared. Okay, so you get 4 plus 16 that would be the square root of 20. And then they put it in here because you got to do the simplest radical form. So see, the square root of 20, that's square root of 4, square root of 5. That would be 2 square root of 5. Okay. And that's what you want for your final answer. Or you could take the 20 all the way down, like we've been doing, to 2 2s and a 5. So you either stop there because you know that's a perfect square, or you go to the prime factorization because you know that is. So the 2 comes out, and then the 5 stays trapped underneath. All right, so that's page 1 of the Radical Expressions and Equations worksheet. So a lot of that you already know, but we're just extending it and filling in a few of the gaps